Hi, everyone. Welcome to the Applied Algebra seminar. Today we have Matteo, is it Mucciconi, I think? Who'll talk about symmetric polynomials and integrable probability. He's coming all the way from Tokyo, where it's 5 a.m., so please be a little gentle with him. If there's any questions, feel free to ask in chat, and I can verbally say them to Matteo, or feel free to unmute yourself and ask if there's any questions. And take it away, Matteo.
Okay, thank you very much, Ram. I'm very pleased to be here. And so today I will discuss about some uses of symmetric polynomials in probability and especially in integrable probability. I will discuss mostly. I'm not really too sure about how popular is integrable probability in your group. So at the beginning, towards like maybe 40% of the talk, I will review some generic results, how probability and symmetric polynomials are related to each other, and then I will discuss some of my results. Okay, so the philosophy that I adopted in my research in the past few years is kind of summarized in these three bullets. So it is known that probabilistic systems, especially interacting stochastic systems, can be solved using the theories of symmetric polynomials. There are families of symmetric polynomials which have nice combinatorial properties, and they can somehow come up from theories of certain stochastic systems. On the other hand, you might happen to study other interesting solvable systems, and this study might lead you to discover new symmetric polynomials. And the point is that can you make algebra from probability? It is known that you can make algebra from combinatorics from algebra. You can make probability from algebra. Can you make algebra from probability? And this is some of these aspects I will discuss below. Let's discuss the first example on how symmetric polynomials happen to occur in stochastic systems. If this is too trivial, please let me know, and I can move on. So there is a very simple model, very old model, which is called the corner growth model, and it is shown in the picture here in the left. So you consider a grid of cells, and you assign to each cell a number, which is Gij, and this number is sampled randomly, and the distribution is given by a geometric random variable depending on a product of two values, xi and yj, where we assign to each row a value y, y1, y2, y3, and so on, and to each column a value x1, x2, x3, and so on. And this gives you your random environment. And then you consider on this random environment a special model where you have a shaded area, gray area in this picture, and this area expands by absorbing the cells, which are only corner cells. And the absorption time for each corner cell is given by the random variable Gij. So you see that with time, this gray area will grow, and so you can think of this as a growth process. And a very natural observable to study is the first absorption time. That is the first time a cell gets absorbed by the gray area. We call this random variable Tij, where I and j is the value of the cell. And it is almost obvious to see that this Tij has this precise formula. So you can consider a path starting from the first cell and moving up until ij. In this case, I and j are equal to 5. and then you collect all the waiting time along your path. Then the waiting time Tij, the first absorption time Tij, is the maximum time that you can collect with such an upright path starting from the corner cell. So this is pretty standard, and so we might ask ourselves, what is the probability that that the first absorption time at a specific value ij is equal to some number k, and we just expand the definition of the random variables. We take g, so this value here, an environment gij, which means a grid of size I times j, and we consider all the possible events that the first absorption time is equal to k. So this is kind of a summation, and then we can distribute the value of the geometric random variables. We can divide them into x and y and so on. And now combinatorics kicks in, because we recognize that that we can unleash the power of the RSK algorithm, and see that if you consider a grid of integers, and you are looking to, I mean, you are all interested in the last passage time or the longest increasing subsequence, then we can resum this summation here into a summation over partition over pairs of tableau P and Q of the same shape, with the condition that the longest increasing subsequence of this matrix here has exactly length k, which following the RSK algorithm implies that the shape of the shape of the tableau P and Q is exactly as first row no longer than k, and then we recognize that these two terms gives rise to the sure symmetric polynomials. So this is a first example, very very popular example on how sure symmetric polynomials happen to be closely related to a model which is very simple. And of course, here we are only asking for 1 point distribution, but we might be interested in the joint distribution of absorption times along, for example, a segment. And in that case, the model is still solved by sure polynomials, but requiring a different condition on the partition. So this is what I presented to you now is an exactly solvable model in the KPZ universality class. The Kardar-Parisi-Chang equation is a stochastic PDE, but I will not discuss that here. Just suffices to know that the growth process that I presented above is part of a larger family of growth processes which have been studied in the last 20 years, and that are universal in the sense that their properties hold for asymptotic properties, for example, scaling or fluctuations. They hold universal in nature. So these exactly solvable models in KPZ class are of two types. The one that I presented above is usually referred to as zero temperature, because you can use sort of bijective combinatorics to recast a probabilistic system into a problem on symmetric functions. And in this case, you usually have determinantal point processes as a result of tools like Lindstrom, Jessediano, Lemma, for example. On the other hand, there are probably more interesting models, which are models at positive temperatures, for which this classical these classical tools are not available, and so in these particular cases, symmetric polynomials enter the story in different ways that I will review. So let's discuss what is a McDonald process. McDonald processes were introduced in 2011 by Borodin and Corwin, building up on some older ideas, and the idea is that we want to study growth processes in 2 dimensions, but maybe growth processes in 2 dimensions might be recovered as projections of more general growth processes in 2+1 dimension, in 3 dimensions, let's say. And how do we construct the McDonald processes? Okay, so there is this problem with the video. So McDonald processes are have this form that I'm showing here on the screen. We consider a sequence of partitions, mu1, mu2, mu_n, and so on, and we associate to a specific sequence of partition this probability given by a product of skew McDonald polynomials, and then there is also another McDonald polynomials to complete this product. Here we assume that Q and P are the McDonald polynomials depending on 2 variables T and Q. I'm assuming familiarity with McDonald polynomials because I think that most of you are familiar with algebraic combinatorics. And let's see what happens if we create such a measure and we take sequentially. So in this video that I'm showing here. Oh no, you cannot see the video. Okay, unfortunately, you cannot see the video. Let's see if I can.
Well, you have to change your the sharing. You just share the other thing.
I think now you can see this simulation.
Let's see.
On the screen.
Oh yes, we do.
Yeah, now it's okay.
Okay, so okay, so if in this simulation that I showed to you, there is a growing surface which is represented by this. Let me show it to you again. So we see that at each one of these lines represents a partition in the probability measure that I showed to you. For example, the bottom particle is a partition of only 1 element, which is mu1. The second row is a partition of 2 elements. In this, let's show again this video, and so on. So we see that we have a sequence of interlacing partitions, and why are they moving? Because I'm taking different frames by updating the value of the variable y. So if I take y1 and then I take a screenshot, and then I take y1, y2, and then I take another screenshot, and so on, this generates this nice dynamics that I have showed you. So we can say that this function here encodes the time component. Okay. Okay, so these are the McDonald points. Why are these McDonald processes interesting? Is that if we only look at the case when either parameter t equals 0 or q equals 0, then it happens that there are 2 special points of this special projections of this process that are interesting for physicists. For example, if we take only a look at partitions on the rightmost diagonal or on the leftmost diagonal, they happen to be autonomous Markov processes, which which are models of growth, which are generalization of the corner growth process that I showed you at the beginning. And they have some names. For example, there are Q-taceps, Q-post-taceps. This is important in physics, is the 6-vertex model, although in this case we are taking a special case, it's stochastic with 6-vertex model and so on. You might be familiar with these models or not, but they have been studied in the last 10 years, especially these models have given a number of results. So why McDonald processes are relevant? You are just basically throwing a lot of functions on the screen, and then you're saying that this probability is nice. But can we say anything about these processes? And the answer is very simple, yes. So there are special observables that are easy to study. For example, we know that the McDonald polynomials, they enjoy this nice Cauchy identity, which we might think as a partition function if you come from statistical mechanics. And McDonald polynomials also possess families of operators that act diagonal on them. Therefore, combining, and we call d lambda the eigenvalue, which happens to have this form in this case. And so we, assuming that, so remembering that this part here can be thought as a probability measure once we divide by pi of xy, we can evaluate the average of this observable given by the eigenvalue by simply applying the eigenoperator on the partition function. This is something very basic, and then from here you can start to think how to make something physically relevant out of this observable. So McDonald processes are solvable in this sense, and so what I just showed you is just a way to utilize symmetric polynomials to solve stochastic processes or to generate stochastic processes. But there are also other ways to utilize symmetric polynomials once you try to solve a stochastic system, a stochastic particle system, and this comes from physics, and it's called Bethe ansatz. So assume that you have a Markov operator H, which is the generator of a stochastic process, a Markov process x of t. So you can imagine to solve this problem if you can diagonalize the Markov operator H. To do so, this is usually a very difficult task. Diagonalizing matrices in general, there is no, especially if they are not symmetric, there is no. I mean, I don't know of any general theory, but in the 20s or in the 30s, I think, Bethe came up with an idea to diagonalize Hamiltonians in that case by using an ansatz, and if the Hamiltonian happens to satisfy certain rules. But so the Bethe ansatz eigenfunction are called here denoted by psi left and psi right, are usually symmetric polynomials in the z variable, and therefore if you try to solve a stochastic model with Bethe ansatz, you are already assuming that symmetric functions are relevant to you. In the KPC class, relevant families of Bethe ansatz eigenfunctions are the Spin-Littlewood polynomials, which were symmetric rational functions. Okay, they are not really polynomials, but this is not really important. Which were defined by Borodin in 2014. But these types of techniques have also been explored in the last maybe 15 years, and this is a list of notable authors which have given contribution. Okay, so the point is that so there are these two methods to arrive to symmetric polynomials, starting from a stochastic process, and these are the McDonald processes. You can solve a system by somehow embedding it into a higher dimensional growth process, or there is the Bethe ansatz. There are models which are solvable by McDonald processes, and these are this model, for example. But there are in general models which are solvable by Bethe ansatz, but not by McDonald processes. So my question when I started a few years ago, the PhD was, does there exist a more general family of polynomials, more general than the McDonald polynomials, such that you can always solve a stochastic model, for example, one of those written in red? So does there exist a model with a family of polynomials such that each one of these models can be obtained as a McDonald processes, but instead of McDonald polynomials, we need to take another family of polynomials? And this question was also asked by these authors in a paper. Okay, so this is the question. So does there exist these extensions of McDonald processes? Or if you come from algebra, does there exist a family of polynomials more general than the McDonald polynomials that is useful in probability? Let's see. And the answer is yes. And it comes in the form of a new family of polynomials, which is called spin Cubicle polynomials. Oh, maybe I should say now that we are trying to generalize. So there are the McDonald polynomials, and they depend on two parameters Q and T. And I have said that only when wholly tooled case Q equals 0 and Cubicle case T equals 0. Only in these two cases, this model turned out to be nice probabilistically. Well, there are also other cases, but today I'm focusing only on these two. So I'm not really trying to generalize the McDonald polynomials with two parameters, but I'm trying to generalize the wholly tooled polynomial on one side and the Cubicle polynomial on the other. And then maybe there is something above, but this is still an open question. So let's describe this family of symmetric polynomials, and then first I will define some of the. I will define these polynomials, and I will state some of the properties, and then if we have time, I will check on their probabilistic application. Okay, so we stopped at so I finished basically my review of potential uses of symmetric polynomials in probability, and I also asked a question. The question was, does there exist this generalization of partial generalization of McDonald polynomials in such a way that we can construct every solvable model in the KPC class as a projection of measures built on these new polynomials? And then I'm going to describe some combinatorics, some algebra. Now let's define the Cubicle symbol, which is this product here. You take a complex variable z and a number q, which is fixed throughout, and we define the nth Cubicle symbol as this product of n terms. And using this Cubicle symbol, we define a branching factor. You don't really have to pay too much attention to this branching factor, but just you just know that that we are defining a function f, which depends on a single variable x, and this function is labeled by partitions lambda and mu, and this partition have the property of interlacing. So just as we have seen before, so this is if this is lambda, then mu will interlace with lambda, meaning that there are this relation. Okay, so this polynomial here can be used as a branching factor to generate multivariable polynomials, which can be labeled by either two interlacing partitions or a single interlacing partition. And this expansion here is the branching rule. Now, before I move on, I want to say that I'm not really the one who thought first of this family of polynomials, and I will describe first. I will describe later where do they come from. But they were defined first by Borodin and Wheeler in 2017. But there is a curious fact. I was working with Leonid, with my co-author, on these polynomials, and there was a mistake in the code, and I coded these polynomials with the product stopping at k, where k is the length of mu, but the original polynomials were in the original polynomial this product would stop at k+1. And somehow this mistake gave rise to a number of nice properties of these functions. For example, we will see that they enjoy eigenrelations and many other things that the original spin-cubic polynomials would not enjoy. So I'm kind of confessing here that some of these results come out directly from a mistake, but somehow this mistake was miraculous, and these polynomials that I will talk about are actually nicer than the original one of Borodin and Wheeler. So let's see why have I defined those polynomials, and where do they come from? They come from the theory of the Yang-Baxter equation for the case of the UQ-SL2. UQ-SL2 Yang-Baxter equation, and if you study this the R matrix of this Yang-Baxter equation, and you apply a procedure which is called fusion, you come up with nice factors. So this R matrix becomes factorized, and these factors have this form as products of Kupo-Hammer symbols. Then, because we are studying we are building up a theory on the R matrix of UQSL, and we can expect that our functions will be symmetric because of the Yang-Baxter equation. So the Yang-Baxter equation is an identity of this form here. You assume that there are three kinds of weights. Maybe I can zoom. There is the dark blue weights, there is the light blue weights, and there is this cross weight. And each one of these weights has the form of this is more or less similar to this factor here. Then if we take the summation over internal states k, k1, k2, k3, then this rational function here on the left hand side will be equal to the rational function on the right hand side. But the rational function on the right hand side, we see that the configuration of vertices has been exchanged. So the dark cross came below, and the light cross came above, and then the crosses, the diagonal cross passed through pass to the other side. So this is an identity between rational functions, but this identity implies that if we build up functions as partition functions using these weights, for example, as in this case, and we create this partition function in this form. For example, we can set, just to keep the color consistent, we can assume that there are two rows, and each one of these vertices is assigned a weight W, and each one of the vertices above is assigned another weight W, but with a different parameter. So here we have Y, for example, and here we have X. This defines the functions fxy and fyx, and as a consequence of the Yang-Baxter equation, I can add a cross here and then drag the cross, swapping parameters as the cross gets to the right. The Yang-Baxter equation guarantees that these branching factors will be symmetric with respect to the exchange of variables. This is some sort of standard procedure, but its uses in the theory of symmetric functions is not too old. And so we have generated a family of polynomials, which I recall are this function f here, and here we have a scheme of these symmetric polynomials, which depend, as probably you have seen before, from two parameters, depend on two parameters, x and s, because the fundamental weights depend on these two parameters. And by taking scaling limits of these parameters, we recover a number of other functions. For example, the trivial choice is taking s equal to 0, and in this case we recover the Cubicle polynomials, which we have discussed maybe earlier. And another nice choice is if we scale s and also the variables x in this form, in which case the spin-Cubicle polynomials become the Grothendieck polynomials, depending on the additional parameter beta. And of course, taking beta to 0, we recover the Schur polynomials which we have encountered at the beginning. On the other side, we can take certain continuous limit where we scale both the parameter s, the parameter q, and then we also scale the labels lambda and mu. In this case, these spin-Whittaker polynomials, they become a new family of functions, which we have called the spin-Whittaker functions, and they depend on a parameter s. And taking the parameter s to infinity, we recover another very classical family of symmetric functions in representation theory, which is the family of Whittaker functions. In the G, of course, there is a GLN case. So why am I showing you the spin-Whittaker polynomials? Because they resemble the Macdonald polynomials in the sense that they admit operators which act diagonally on them. Define the shift operator, the Q-shift operator, which act on a function by taking its height coordinate and scaling it by Q. And we can define also the Q difference operators, D1 and D1 bar. if you're familiar with the theory of symmetric polynomials, you will know that if s goes to 0, then this becomes a McDonald McDonald operator. Which I have briefly discussed earlier, at t equals 0. Also for the dual operator d1 bar, the same is true. Taking its limit s to 0, we recover another version of the McDonald operator. And then we have a theorem that says that these two operators act diagonally on the spin-Whittaker polynomials, the spin-Whittaker polynomials that I have described before. And in particular, the eigenvalues are very simple because they are simply the last component of the partition lambda or the first component of the partition lambda, taken with this strange exponential q to this value. This is a nice result in my opinion, and especially if you, this is why I made that remark at the beginning that Borodin and Wheeler's symmetric polynomials, they would not satisfy eigenrelation, whereas this kind of wrong polynomials, they are nicer because they have this eigenrelation. So now I have a question for an algebra audience, and this is the following. Very important properties, at least, I believe that is an important properties of McDonald polynomials, is that they are orthogonal with respect to a few, two different scalar product, and in particular, McDonald polynomials are orthogonals with respect to the so-called torus scalar product. The torus scalar product here has this form here, where the scalar product of two Laurent polynomials, Laurent functions f and g, is given by this integral on the torus, on the n-dimensional complex circle. Not the product of n different complex circles, and then there is a measure here, which depends on the number of variables and on the parameters q and s. Now, in the case of McDonald polynomials, there exists a measure mqt such that McDonald polynomials are orthogonal with respect to this measure. And McDonald himself, in the book, proves the orthogonality by just, the orthogonality follows from the fact that this measure here is the McDonald operators are self-adjoint with respect to this scalar product defined with respect to this measure, and this yields the orthogonality of McDonald polynomials. An important part of the McDonald's argument is that the eigenvalues of the McDonald operator are all different. So they depend on lambda, but they depend on each part of lambda in such a way that that all the eigenvalues are different. In our case, I have shown you that unless if the eigenvalues were q to the lambda to the minus lambda 1 and q to the lambda n. Therefore, when n is bigger than 2, they do not separate the Hilbert space. Therefore, but we can still try to conjecture something like the torus scalar product for McDonald polynomials holds. And we conjecture that there exists a measure which we guess in this form. There exists a measure such that the new operators D1 and D2 are self-adjoint with respect with, and therefore, at least in certain case, when eigenvalues are different, we can prove this orthogonality relation. So this is something rather trivial. This is true for S equals 0, but also for when lambda 1 is different than mu1, because of the self-adjointness, and because of they have different eigenvalues. But then we try something, and we try to say that this conjecture always holds for any partition lambda mu, and this conjecture actually makes no sense because there is no algebraic reason why this should hold, but somehow from numerical tests that I have done, it holds. So, for example, here I'm showing you a screenshot from Mathematica where I've taken this orthogonality here, setting Q equals 0 in such a way that it becomes just a sum of poles of residues on a finite number of poles. When Q is larger than 0, because of the Q-Pochamer symbol, not bigger than 1. When Q is bigger than 0, the integral becomes only numerical results are available, and they're very, very hard. But also in that case, this conjecture, surprisingly, I was not able to disprove this conjecture. So this means that by purely reasoning from a probabilistic standpoint, we have found something nice, which might have some nice algebraic meaning. And
can I ask a question here?
Yes, please.
Do you have is it the case that the power sums are orthogonal with respect to the scalar product?
So in the theory of McDonald polynomials, there are two types of scalar products. There is the whole scalar product, which is the one that makes the Schur polynomials, for example, orthogonal. Yeah, the one defined on the Fock space. Yeah, I think PM.
Yeah, but the power sum are also orthogonal for the other scalar product of McDonald. So what Mike is asking you is that if you put the power sum there, is it orthogonal, not necessarily orthonormal?
Okay, so I haven't checked this.
Because usually this is one way to define that scalar product. Is the way you start defining that scalar product is you're defining on the power sum, and then you extend it. You understand that kernel that is generated by the power sum.
Okay, so I don't know this. I knew this defining property for the whole scalar product, but I don't know the relation. Maybe I'm just ignorant, but I don't know the relations between the whole scalar products and the torus scalar product. So I will certainly try. So
yeah, it's a good one to start off, because one of the definitions of McDonald polynomials is you say, here's a scalar product which is defined on the power sums. I know nothing more about it other than the scalar product exists, and you say you want something which is orthogonal and triangular with respect to another basis, and that's a definition of it. And so it looks to me like if you have that property on this scalar product as well, you might be able to do the same, and then get say a purely algebraic definition of it.
Okay, so thank you very much for the suggestion. So I will certainly try. I will certainly try to to see if something like this would work. I'm very curious.
And just more comment while we are there, because looking at everything you did, first of all, McDonald had two family of operator, and one operator had distinct eigenvalue, like you mentioned, but another operator has not distinct eigenvalue, but had other kind of properties. So my question is, have you tried to change your operator a little bit so that you will obtain distinct eigenvalue?
I have tried numerically. Let me go back to the eigenvalues.
Because I kind of remember vaguely, Mike can correct me if I'm wrong, that the one for which he has distinct eigenvalue is obtained by taking, like this approach of triangularity with the power sum.
Mm-hmm.
I forgot.
I don't remember.
I have to be honest, but so I don't have a good feeling for algebraic feeling for this polynomial. So all I usually do is to try numerically and see if it works. And yeah, because my question come more from probability. Yeah.
And then my other comment is, so McDonald kind of put a more algebraic framework and operated theory of some polynomial that were defined by Kevin Cadell earlier a little bit. And for some reason, I have the impression that your polynomial are closer to the one of Cadell than McDonald. And the way Cadell defined it is exactly through some integral form with product and stuff like that. Yes. No, one L at the end, I think. Yeah, K Cadell. So maybe you should look it up to see if there is some link with your function, because then you will have directly that scalar product for which it's good.
I was thinking that these functions are similar to to Kornwinder polynomials, but yeah. I don't know about.
Well, Cadell is a little bit kind of the origin of the McDonald polynomial. McDonald's read that paper and said, "Oh, this is interesting, but it's not the right formulation," and then reformulate everything from that.
Okay, so I will certainly try to deepen my knowledge in this thing. Thank you very much.
Again, it's I'm not even certain it could hurt, but just from memory like that, it kind of ring a bell that maybe what you're doing is more closer related to that than the other.
Okay, very good. Yeah, so the message I'm trying to convey here is that somehow these polynomials, they make perfect sense from an integrable probabilistic standpoint, and but they happen to have some surprising properties that I cannot explain. One thing I can say is that if you take the Grothendieck limit when f lambda becomes g lambda, or g lambda is the polynomials, Grothendieck polynomials depending on beta, then this scalar product here becomes something that I haven't been able to find in literature, but it was pretty straightforward to prove directly. So yeah, there is also this other case which is possible to prove. Not only the McDonald case, but also the Grothendieck case. So, but for example, in this slide that I'm showing, there is this slide does not include none of these two cases. Okay, so let me just go through how the spin-cubic polynomials appear are useful in probability. And for this, we need basically 3 steps. We consider again the Young-Baxter equation, and we consider the Young-Baxter equation as a summation, as an identity between 2 summations. And when we have where on the left-hand side we have all the possible terms that come from a variation of K1, K2, and K3, and the right-hand side similarly. All the terms that come varying K prime 1, K prime 2, K prime 3. And when we see a summation of identities, an identities of summations, we can imagine that that we can construct a probability measure, which sometimes called bijectivization, sometimes called probabilistic bijection. And this idea was introduced by Buffetov and Petrov in 2017, which is an attempt to make sense of these weights here as transition probabilities. And this means that we want to construct a coupling of right-hand side weights and left-hand side weights, and we want to construct a probability measure, which we call P, with this notation, in such a way that if we take the product of P times the left-hand side weight, and then we take the summation over K prime, we obtain this because this is a probability measure. But at the same time, if we take the summation over K, we obtain the right-hand side weight. So this is something which is in probability called a coupling. And in this particular case, we consider the Yang-Baxter equation with the weights that are given in this slide. I'm not really asking you to check this weight, just to confirm that the Yang-Baxter equation is just to be precise about what the tools that I'm using. Okay, then we have this from the Yang-Baxter equation, we can define probability jumping, like kind of transition probability from a state where the cross is on the left to a state where the cross is on the right. We are imagining that this cross here is traveling through like two horizontal two lines of vertices stacked on top of each other, and this cross travels to the right, and each jump that this cross makes is weighted by a probability distribution built on the Yang-Baxter equation. And therefore, we can construct a probability distribution on full lines. We can start from states given by a partition lambda, and states given by a partition mu, and then we can update the intermediate states. In this case, they are given by partitions kappa and nu. And what we obtain is pictorially described by this rectangle here. So we fix boundary states lambda and mu, and we sum over we transition from a partition kappa to a partition mu with this sort of rules described by the Yang-Baxter equation. And then finally we can build like a full field of random diagrams starting from an empty configuration, and then we apply these global moves sequentially, generating a random field of Yang diagrams. And
hey, Matteo, it's been about 25 minutes as a heads up. So if you can start finding a nice place to wrap up.
Okay, I think I can finish. So yeah, so basically what I wanted to say is done. I just want to mention that that in this case, the probability distribution, if we take a look, remember that at the beginning we looked at the corner growth model. The corner growth model corresponded to lambda 1 of a Schur measure. And in this case, if we look at lambda 1 of a process weighted by spin-Cubicle polynomials, we obtain a growth process like the one described here in this picture, where we see where the blue numbers are the height function, and if we go in this direction, we are basically climbing up a random stair, and this becomes another stochastic integrable systems, which is called the highest spin vertex model. Okay, so I can finish. This is the hierarchy of models, which are to which the spin-Cubicle process sit on top. But okay, I can probably finish here. And yeah, what I wanted to discuss with you are these things which on which I already received some comments. Some already very happy, which is why on Earth would some polynomials that I just described, that I just defined by mistake, satisfy some seemingly nice orthogonality relation. Okay, so thank you very much for your attention.
Thank you.
Awesome. Thank you very much. Let's give a round of applause. Awesome. Are there any questions?
So can I ask?
Go, Tom.
So you skipped over all the KPZ stuff that you were going to talk about. So could you just tell me how these new processes fit into the fit with the KPZ fixed point and into that hierarchy?
Okay, so I told you that I can build up a field of random diagrams by playing with the Young-Baxter equation, and then what happens is that I can build up a measure, as I did before with the McDonald polynomials. If you remember with them, if you remember with the McDonald polynomials, I build up a measure by taking products of a number of McDonald polynomials, a number of skew McDonald polynomials, and then the dual function was giving the model like a time direction. By increasing the number of variables, I was finding the time direction, and I can do the same also with this spin-Cubicle processes. And in this case, I generate a random interlacing array, or more in general, a random field, which is given in this picture, a random field. To each vertex we have a partition. For example, if I take partitions along a segment, I see this interlacing condition. And then if I look at these diagonals, the leftmost diagonal or the rightmost, the extreme diagonal, I see the emergence of some models. Some of them were known, some of them were not. Some of them were already related to symmetric functions, some were not. And for example, if we take a look at the lambda 1, the one that was corresponding to the corner growth model in the Schur measure. Corner growth model is very popular because it's determinantal, it's exactly solvable, and as you mentioned, it was also used to derive the KP, to exactly describe the KPC fixed point. But if we take a look at the generalization, the two parameters generalization, but with S and Q equal 0 in this case, but if we free up S and Q, we obtain this random growth model which becomes a stochastic vertex model, and each one of these vertices is weighted by a probability distribution, which is given here. It's not illuminating to look at this these probability weights. It's just that they nicely generalize corner growth model and then simple exclusion processes in a unified fashion. I mean, they unify these models, but so the problem is that this process here that is shown here, it's solvable because I can compute observable and maybe take asymptotic limits, but it's not determinantal. So the corner growth model is important because it's determinantal, but this is not determinantal. So it's harder to study, and yeah, it is a challenge to study this model more in detail, depending how much you are interested in going in depth into solvable models. But it is a challenge to describe this model in detail.
I think, is that okay, Tom, or?
Yep, thank you.
I think, Mike, you had a question as well, or?
Yeah, I was going to ask if you have if you observed it's like positive or monomial positive or something. For representation theory and algebraic combinatorics, you kind of want to see some sort of positivity results where you say, if you expand it in the Shor basis, then you've got these coefficients.
I have some comments there. Let me go to this slide here. So one thing that I have to say is that this P-cubic polynomial, if you take the monomial expansion, the monomial, I mean, these are rational in S. So you will have, for example, I don't know, x1, x2, and then 1 over 1 minus s squared, something like this. So this is not very nice. So maybe we want to try to kill the s variable. Well, we can kill the s variable by sending it to 0. But if we send it to 0 with this scaling, then okay, we do something trivial because of course the Schur expansion of Grothendieck polynomials is known. But maybe we can do an intermediate expansion where we take the parameter q, we take the parameter beta, but we send s to 0. And maybe you can call this family q Grothendieck polynomials. Who knows? And in this case, I find that I can expand. Maybe let me see. This is just a numerical experiment. I couldn't prove anything for this polynomial. So let's call this new family q Grothendieck. Okay, so we have this family, and it turns out that let's call them G. And it turns out that I can do G lambda. I can expand G lambda as some coefficient G nu lambda of P nu, where this is the Cubicle polynomials. And therefore, because the Koska polynomials for the Cubicle polynomials is known, I can also do this. I mean, conjecturally, I have some exact formulas, but I couldn't prove them. So this is explicit. And therefore, there exists also coefficient C, eta lambda S eta. And these are also explicit.
And do they depend on Q?
Yes, they depend on Q. They depend on Q and on beta. C. They depend on Q and on beta. Well, the dependence of beta is kind of trivial because it's just a power at the beginning. But then there is the dependence on Q, which is non-trivial. It becomes like a summation over flags. It's the summation is closed, like it fits like a less than a line, but then I couldn't prove this property. So yeah, there would exist like a Q Grothendieck limit of these polynomials, and maybe in this limit algebraic structure are more apparent. Who knows?
Does that agree with the standard Q Grothendieck symmetric functions? So there are some in the literature.
Yeah, I have tried to look at there are a number of Q deformations of poly, but I don't think that so I found a deformation where the Q Grothendieck polynomials were still determinantal. But this is not determinantal, definitely not. So I don't know. Maybe you are referring to something that I cannot that I don't know. Although I tried to look in literature if this limit was already considered, but I could not find anything that would fit the formulas that I was getting. So yeah, I don't want to claim that these are new functions, but I haven't found them.
Are there any other questions? All right. If not, Matteo, do you want to unscreen share? And then we'll thank the speaker again when, yeah. So we'll thank the speaker again. So next week is reading week, so we won't have a talk on Monday as a heads up. And that's it. Thank you, Matteo, for the good talk.
Thank you very much. Thank you for the comments. I will try to look into each of these comments, and yeah, have a nice evening.